Why do self-intersecting quadrilaterals behave unexpectedly? Imagine drawing a four-sided shape where the sides cross over each other like a bow tie. It might look interesting, but it also behaves quite differently from the shapes you usually see. That's because these shapes are called self-intersecting quadrilaterals or crossed quadrilaterals. They are not your typical four-sided shapes with sides that stay separate. Instead, their sides cross, making the shape more complex and surprising in how it acts. In a simple quadrilateral, like a square or a rectangle, the four interior angles always add up to 360 degrees. The shape can be either convex, where all angles are less than 180 degrees, or concave, where one angle is more than 180 degrees. But when the sides cross, things change a lot. The total of the interior angles jumps to 720 degrees because two of the angles are reflex angles, which are bigger than 180 degrees but less than 360 degrees. These reflex angles seem to be outside the shape, but they are still counted as inside angles in the math. Another unexpected behavior comes from the diagonals. In simple shapes, diagonals usually cross inside the shape, but in self-intersecting quadrilaterals, both diagonals stay outside the shape. This makes the shape behave differently when you try to find its area or measure its angles. For example, the usual formula for area, which involves the diagonals and the sine of the angle between them, becomes more complicated or doesn't work the same way. There are special types of these shapes, like crossed trapezoids, where one pair of sides is parallel, or antiparallelograms, where opposite sides are equal. These shapes have unique properties because of their crossing sides. They can look like a diamond or a star, and their properties are different from regular quadrilaterals. In real life, understanding these shapes helps in fields like engineering and design, where crossing lines and complex shapes are common. It's important to remember that formulas and rules for simple quadrilaterals don't always apply to these crossing shapes. For example, calculating the area or understanding the angles needs special methods. So, the reason these shapes behave unexpectedly is because their sides crossing over changes the way angles, diagonals, and areas work. They don't follow the usual rules because their structure is different. Recognizing these differences helps us see why they act in surprising ways and appreciate the variety within the family of quadrilaterals.